Today, I will give you brief ideas about different phases in condensed matter. So when you talk about phase and different phases of matter, first of all, we need to understand what is phase. Yeah. So if we try to give a definition approach, so then we can call it equilibrium state of matter whose properties, qualitative, do not change with small changes of external parameters. So this is basically the definition of a phase. So how to give an example? For example, you take a bottle of water, and in this water you just for example, the temperature of the water, for example 20 degrees centigrade or 25 degrees centigrade, you rise the temperature a little bit, maybe 25 degree to 35 or 40 degrees centigrade, you essentially see no changes of the phases of the water. So that means water is basically a very stable and equilibrium phase. Yeah. And the temperature, what you're rising from 25 to 45 degrees centigrade, is basically a parameter. Similarly, if you take this bottle of water and you try to compress it, yeah, and then you'll see with minimum, with your effort by your strong hands, you'll see that the water remains water. It's not really changing its phase. So that means water is a kind of stable and equilibrium phase. So that's the thing. So the second one can tell one can define in that way, that stable under infinitesimal parameter changes. So here, as an example, I told you that you can change the pressure or you can change the temperature. So third thing, within a phase, the thermodynamic potential varies in an analytical fashion. Yeah. So it will not show a very dramatic or drastic changes. Yeah. So phases can be characterized by their symmetries. This is important. And more precisely, the symmetries of their density operator. This is bit technical, but in principle, your phases can be identified by their symmetries. And of course, the different phases are separated by the phase transition. For example, you have a gas to liquid phase or liquid to solid phase. For example, if you take water, water becomes ice. This is a phase transition. So how many phases we see? In general, when you talk about the phase transitions, we talk about four phases that we often talk about. Yeah. So these four phases are solid, liquid, gas, and the plasma. Yeah. So how do you go from one phase to another? For example, you have to change the enthalpy of the system. Yeah, that's a bit technical term, but that is you usually follow. You can go from solid to gas, or gas to solid. If you want to go from gas to solid, you have to do deposition. When you have to go from solid to gas, you have to make a sublimation. If you really want to go from liquid to solid, you have to make directly freezing. Solid to liquid means you have to do melting. If you go liquid to gas, that means you have to do vaporization, or gas to liquid, you have to do condensation. And from gas to plasma, you can do by ionization, and by this recombination of your positive and the negatively charged particle, you can come to gas. So therefore, these are the more common known four phases of matter we usually talk about, or usually we heard about. But is this the only phases your nature provides? Yeah, or the system we are dealing with, is this for only phases what we have in our surroundings? The answer is no. So let's see what are the phases we have in our nature. So here, for example, this is a simple phase diagram for water. You know, this is the gas, liquid, and solid phase. So this is the x-axis is actually our temperature, and the y-axis is our pressure. So you can see that this is, for example, our gas phase, and the gas phase, you can have a phase transition, and you can go to a, this is this yellow line is basically the line which shows how to go from gas phase to liquid phase. And then you have a triple point where actually this gas phase, liquid phase, and the solid phase meet together, and then you have a solid to liquid phase. This is the first order phase transition. Liquid to solid phase you can go, and you see there is a line. This is a very fast order phase transition. So that means there is no way that the critical end point of your solid to liquid phase. But on the contrary, if you see your gas phase and liquid phase, so this is the first order phase transition line, but there is also a way one can reach, for example, above 647 Kelvin and pressure of something 10 to the power 8 Pascal. You can basically cheat this line and you can go follow the path C. So there, essentially, you don't really see a phase transition, only your density will change. So that's the critical end point, or the critical point, we can call it. But in the solid line, you see there is no, at least so far, available data suggests that there is not really any the existence of any critical end point. Yeah. So, but this is not the only phase nature provides. There are many phases, states, and many phase transitions in nature. So we commonly talk about magnetic phase. We talk about the superconducting phase, and within the superconducting phase we talk about pseudo-gap state and the in-gap states. We talk about superfluid states, and then we talk about the Bose-Einstein condensate. This is often referred at the fifth states of matter, and we talk about quantum phase transition, nematic phase, usually nowadays widely discussed in iron pnictides, for example, and then quantum spin liquid states. But there you don't really see any symmetry breaking. No conventional symmetry breaking is there. But in all other phases, what I talked here, more or less you have a symmetry breaking. So many more complex and rich phase diagram you can find in condensed matter physics. In one way, one can tell that modern experimental condensed matter physics largely dealt with investigation these complex and rich phase diagram. So I would just like to give you a few examples how the phase diagram in modern condensed matter physics usually people we are dealing with. Those who are interested, of course, who can follow further or more detailed phase diagram. So for example, here, this is essentially, you can call it as a electronic phases. What you have, this is, for example, a system of cerium palladium to silicon 2. In this cerium palladium to silicon 2, you have x-axis, I have a pressure, and the y-axis, I have a temperature. And then, for example, if you take in a zero pressure, you have a magnetic phase transition, antiferromagnetic ordering phase is taking place around 10 Kelvin. But as you are lowering the temperature by applying pressure, you see close to 2.8 gigapascal pressure, you suppress your antiferromagnetic ordering and you get a superconducting phase. Yeah, that's quite rich phase diagram. Yeah. So one can also think about, for example, I have a ferromagnetic system, yeah, and you suppress this ferromagnetic ordering by applying pressure or some kind of doping, and you suppress your ferromagnetic ordering around 0.9% of some kind of arsenic doping. You suppress your ferromagnetic ordering. So this is also another kind of electronic phases. You can talk about more general phase diagram. This is, for example, a phase diagram of a continuous quantum phase transition. What you do, you have an ordered phase, and then you have a disordered phase. And then this is essentially a classical phase transition. And this is my temperature, y-axis, and this is some kind of parameter R. It can be pressure, it can be some kind of stoichiometry, it can be field. And so what you are doing, you are suppressing your ordered phase, and your suppression in the ordered phase, you send it to t equals to 0. So that means you suppress your transition to at t equals to 0. And then you call it some kind of quantum phase transition, because at t equals to 0, you essentially, your classical effect do not play a role anymore there. But of course, you cannot reach experimentally at t equals to 0. Theoretically, you can talk about it, but experimentally, if you really want to reach, you can only go close to it. So therefore, there are experimental signatures you will find relevant for this quantum phase transition. There are many more phases. For example, this is the phase diagram, which tells about your different interaction, and many things you can get. You can get spin liquid, quadrupolar, and topological insulator, semi-metal. So it's a very complex and rich phase diagram. Depending on your interaction state, you can go. You can go furthermore. For example, this is a phase diagram of both combined electronic and structural phases are involved. You have, for example, nominal fluorine content. This is 1111 superconductor, and this is the superconducting, and this is the transition temperature till nil. That means the antiferromagnetic ordering, structural transition, nil transition, and also the superconductivity. So you see, you suppress your superconductivity, spin density of magnetic order, and then you end up with a superconductivity. Yeah. So this is also very rich phase diagram one can draw. So you can go more. So for example, this is a very recent from 2014 combined electronic and structural phases. And in these phases, you see you have a superconductivity, you have stripe magnetism, you have pneumatic fluctuations. So all these things tells you that the modern condensed matter physics studying modern condensed matter physics essentially also studying all this complicated phase diagram and complicated phases, and try to understand from both theoretically and experimentally how all these phases actually emerges, because this also connects some underlying physics. Yeah, so therefore understanding these phases and complicated phases and phase diagram are an integral part of modern condensed matter physics research. So I hope you, if you really want to know more about this subject topic, then you have to go through all details and so on. So this is just to give you a very brief introduction about how all phases in condensed matter physics are important. So thank you for your attention, and